Baker testing now exists, but I'd been hired in by Bruce Sylvester to replace David Holt. And I heard that they needed a metallurgist. I needed some consulting, so I go down to meet and interview with Bruce about 1979 maybe. And Bruce says, well, I'm paying Dr. Holt $10 an hour, but I'd be willing to pay you $15. And I said, well, right now I consult for $50 an hour, but I'd be willing to work for you for $40 if you got a lot of work. Okay? I'm going to keep looking. When could you start? And I said, start right now if you want. And so he says, well, I'm going to continue to look for another metallurgist, but I'll pay your $40 an hour because he had a month's worth of work backlog. So I knocked out 3 reports, left them for him on his desk when I left that evening, and I come back like 2 days later to finish some more, and he comes in and he says, well, I read your reports and I've decided I'm not going to look for another metallurgist, I'll pay you $40. So anyway, but I was doing about 500 failure analyses a year. And that's how you learn, is you just do, okay? And you see the same thing, after about 100, you start seeing some of the same things come in, right? Just like I was talking about, bad paint jobs, you see the same problem.
That steam corrosion you showed the other day, that
Yeah.
picture in the book was exactly like the picture that you had.
Yeah.
It's like, I've seen this somewhere before.
Now I've done thousands, and anyway. Okay, 8:45. Let's start again. I wanted to go over a couple of things. One is I was looking in the wrong book, that's why I couldn't find it. Here's a plot of monatomic hydrogen and diatomic hydrogen and how much gets absorbed in different parts of the weld pool. This is the weld pool width in millimeters, so you're talking a centimeter on either side. And this is just a theoretical calculation for diatomic hydrogen. It doesn't really absorb very well in the weld pool, but thermodynamically, in the cooler parts of the weld pool, monatomic hydrogen goes in and gives you your 30 parts per million. So it turns out it's monatomic hydrogen. The reason I like this plot, it was done by Steve Gideon, one of my graduate students, but I gave him the idea. Anyway, we ended up winning a Best Paper Award for the Welding Journal that year for that paper. And it had to do with a 2-temperature plasma, okay? Did you know fluorescent lights are 2-temperature plasmas? Anyway, when you take the module on fusion welding, and I talk about arcs and stuff, you'll learn about 2-temperature plasmas. You'll learn, that's why I call it the fluorescent light lecture, okay? Because it tells you how a fluorescent light works. I did want to mention some of these other strength levels. I told you that HY 180 was developed by the Navy, but no one uses it. Why? Because it would have a tensile strength level. It's HY 180 yield. It would have a tensile strength of about 220, and we're getting down to 1 part per million of hydrogen can do the damage. In fact, if I'm the Air Force and I make an aircraft landing gear, I'm going to be using 240 KSI or even 280 KSI super duty alloys, some of which are not all that different from HY 180. They're high cobalt alloys and stuff in order to get the strength. So it's sort of the same technology. There's AF 1410, which is a 10% cobalt alloy. And there's certain things cobalt does with hardenability and the martensite temperature and stuff that if you really want to get really high strength steels in bulk form, use lots of cobalt, which is very expensive, but you can get 280 KSI steel. But you get to 300 KSI, half a part per million hydrogen can destroy your steel in terms of hydrogen cracking. Well, it turns out if I just make a heat of steel in a steel mill, and I don't do anything special with drying this stuff off, I might get between 1 and 3 parts per million hydrogen in that steel just from the grease and other things that are on the scrap steel that I throw into the furnace. I was at a steel mill once and it was raining outdoors, and they came in, the magnetic crane grabbed about 5 or 10 tons of scrap and it was moving it over indoors to put it into the hot furnace, and water was pouring out of it. It was raining outdoors. And water was just pouring out of it into the steel furnace. Okay? So that's how you get 3 parts per million hydrogen in your steel, in regular old steel. Doesn't matter if you're talking about structural steel or bridge steel. or automotive steel, because you can tolerate, it's almost impossible to hydrogen crack that. But if you want to start going to high strength steels, you got to start worrying about that. You actually have to either vacuum degas or electron beam melt or something after you've made the steel to get it down to, actually vacuum degassing will get you down here. You have to melt an electron beam in a vacuum to do this stuff. And that's what they do. They use vacuum arc remelting, so big expensive jet engine alloys and stuff, high strength steels, very high strength steels, ultra high strength from, you know, compared to anything you'd use in a ship. They have to do vacuum arc remelting, double vacuum arc remelting, okay? And this is adding 2 and 3 times the price of the steel, because you're melting it not just once, you're melting it 3 times, okay? But that's what we do if you really want to get high strength, okay? And it is because of hydrogen and hydrogen cracking, okay? Now, turns out hydrogen, this comes out of, actually this was originally out of Coe's book. You knew it was Coe, Frank Coe. It's now, can't remember who, it's in a second edition. Frank Coe retired in probably 1980. Very nice guy. The next guy is not quite so nice, but anyway. This is diffusion of hydrogen versus temperature in steel, and lattice diffusion, just going through the crystal lattice. Hydrogen can go through there fairly quickly. For ferritic materials, it turns out, this is lattice diffusion, which really is extrapolated from much higher temperatures. But in ferritic materials, body-centered cubic materials, you actually get approach lattice diffusion. What is 10 to the minus 4, 10 to the minus 5 centimeters squared per second? Well, when I do the heat flow part of welding in the fusion welding module, I'll teach you about thermal diffusion, but mass diffusion, which is atoms as opposed to heat, goes by the same formula. In fact, as part of my minor degree, I decided I want to do heat flow, and they made me take a course in the math department, which was basically on solving the diffusion equation. Okay? And the diffusion equation can be for heat, mass, momentum. What's the momentum diffusion equation? It's the Navier-Stokes equation. You ever heard of that? Okay, you're going to hear about it. If you haven't heard about it, you're going to get it in spades. Navier-Stokes is a lot more complex because you've got turbulence and everything else. But mass and heat diffusion, you can get down to a very simple formula that the distance that heat or mass travels is always, well, you always end up, well, since you're taking math courses, if you might have an exponential solution, e to the minus x over, I'll just call it alpha t, or x squared over alpha t, okay? That's called the argument, okay? I like to argue, right? So here's the argument of the exponent. You could have an error function solution, which you may or may not be familiar with error functions. An error function is just the integral of the Gaussian, okay? This is the Gaussian, e to the minus x squared. X is a distance, alpha would be the thermal diffusivity, t is time. This alpha squared over xt is sometimes known as the Fourier number for Fourier. So this is just e to the minus Fourier number, actually it's Fourier number squared, okay? Or if you do it for mass, it's called the Fick number, because it's Fick's first and second laws of mass diffusion. It's Fourier's first and second laws of heat diffusion. The second law of each one is a time-dependent solution, and you end up with this. And if you put it all together, it's known as, if you take the Fick number and the Fourier number, you can generically call it the Einstein number, because there was this guy named Albert Einstein who back about 120 years ago looked at this and said, well, all these diffusion equations are all just the same thing. I'm diffusing energy into a material as a function of time, and they always have an argument which is dimensionless. Okay? You cannot take the exponent of something that has units like centimeters or inches or degree centigrade or whatever. It has to be a dimensionless number. So if this is distance and this has units of centimeters squared per second and this has units of time, centimeters squared per second times time is centimeters squared, and centimeters squared over centimeters squared is dimensionless. So this is a dimensionless number. Well, this is centimeters squared per second. This is the Fick constant, 10 to the minus 5. What is 10 to the minus 5? Well, let's take an x where we have 10 to the minus 5 centimeters squared per second. And let's see how far something diffuses in, give me a reasonable time, folks. Someone pick a time. 1 second, 100 seconds? Take something easy that I can take the square root of. 49? Oh no, anyway. Let's take 100 seconds. So in 100 seconds, okay, I have, actually, let's take 1,000 seconds. Because 1,000 times 10 to the minus 5 is 10 to the minus 2. And I take the square root of 10 to the minus 2, I get 10 to the minus 1 centimeters, okay? As the approximate distance that mass or heat would diffuse if I have 10 to the minus 5 centimeters squared per second. In 1,000 seconds is about 20 minutes, something like that, 15, 20 minutes. Okay, well, that's a millimeter, okay? It turns out without convection, if I don't solve the Navier-Stokes equation, I have convection. If I were to release a little bit of perfume in the room, it would diffuse at 10 to the minus 4 or 10 to the minus 5 centimeters squared per second. In stagnant air, that is the diffusion rate of a gas inside another gas. That's about what it is. If I'm talking about mass diffusion, okay, of, carbon and iron might be 10 to the minus 12, okay, down here somewhere. If I'm talking about manganese and steel, it might be 10 to the minus 16 up near the melting point and stuff. These are huge numbers. That hydrogen is going through there just like it's almost a liquid or a gas, okay? And in fact, that's true because I showed you the video from 1950. So those of you who got to class a little bit earlier, and they made the weld and you could see the bubbles coming out almost as fast as it was of the CO2 coming out of the water, of the water in the Sprite, right? Comes out at a similar type of scale. These are tremendous diffusion rates. Still, it only goes about a millimeter in 20 minutes. So now you see why, and it's an exponential decay, okay? So there's your exponential decay. You have some 30 ppm hydrogen. You want to, all of this basically says you'll be at, is it 1 over E? Actually, it's an error function solution. You've got to be at about 4 or 5 times this time in order to get down to 10% of this. So I want to be down to 3 parts per million hydrogen. I better be holding this thing at temperature for getting those types of diffusion rates, holding it at a temperature for an hour or 2 hours. Okay? 4 times 20 minutes is an hour and a half. It turns out if I'm making a piece of steel or a weld and I want to diffuse the hydrogen out, I got to keep that plate hot for something on the order of 20 minutes to get it down to 10 parts per million. I might have to keep it hot for a couple of hours to get it down to 3 parts per million, and I might have to keep it hot for 3 days to get it down to a couple of parts per million. In fact, I can't even get there because there's trapping centers and stuff. But now you sort of get an idea of what we do to get rid of the hydrogen. We can preheat the steel to, let's say, 200 degrees Fahrenheit, so when it cools down, it never gets all the way down to room temperature. I'm at something like this, and I actually get a fair amount of the hydrogen out if I preheat it, and I never cool down all the way until a couple of hours later because I preheated this big mass of steel. If I want to get it down even lower, I may have to post-heat it and do stress relief to get rid of not just the hydrogen, but some of the stresses. And one of the reasons I want to get rid of the stresses is, if you remember, I did this Venn diagram plot of stress, or actually material. I think I had material up here. Actually, somewhere here I actually have the plot. I stole it from a book. Right here. Gee, sometimes it helps if I look at my lecture notes. So material stress and environment. In the center I get stress corrosion cracking. Stress corrosion cracking, I'll explain later, is a form of hydrogen cracking. Okay, they usually have it separate because hydrogen is sort of a very special, just sort of like there's hydrogen bonds and there's van der Waals bonds if you're a chemist. They're really the same thing, it's just one's sort of special. Hydrogen cracking is sort of a special case of stress corrosion cracking. But the point of this plot of the diffusivity, kind of, you can calculate how long you got to keep something hot to get down to these types of levels depending on your strength. And the higher the strength, the bigger the stress, residual stress circle, the bigger the region of stress corrosion cracking or hydrogen cracking. Your environment is how much hydrogen did I put in there to begin with from the welding operation. It has 30 parts per million. That's sort of Coe's plot of, where did I put Coe? Oh, I stole Coe from you. I got to give it back to you. Here, this is yours. But this is Coe. I've got it here somewhere, but this is Coe's plot of the typical amount of hydrogen you get from different welding processes. This, and that's basically practical. This is the kinetics of how fast it might get out of that steel. But I also have to worry about how much residual stress I have, which is what's going to cause this cracking. This environment is sort of Coe's plot of different electrodes and how much hydrogen I put in there. And the material is what's the strength material of the strength level of the material, because that tells me how much residual stress is going to be at my maximum if I have a big heavy weldment and I get full restraint. Okay, so all of these things come together, makes hydrogen cracking very, very complex. It gets very messy, and you need to have someone who can figure out all the different things that go on. There are some other principles of hydrogen cracking that make it sort of, I think it's interesting. Of course, I'm a little perverted, I guess, as a metallurgist and a welding engineer. If I look at, this is out of Coe's book on, and he shows temperature versus a hydrogen-free specimen, what they call a notch tensile strength. Well, the notch tensile strength is, am I ripping the piece of paper? If I have a notch or a welding defect, like in those Liberty ships, I had a notch which weakened the ship in a brittle material. A hydrogen-free specimen, no brittleness, no hydrogen embrittlement. If I have a hydrogen-containing specimen, turns out the worst condition is right somewhere down here around room temperature. Higher temperatures, it diffuses out, just like the CO2 coming out of my Sprite or the hydrogen bubbling out of the weld that you saw the video of. Hydrogen, if I get colder, everything slows down. I get down to this type of situation and start looking at the diffusivities down here at 10 to the minus 10 and start calculating how long it's going to take in seconds to have the hydrogen move around to get to that crack tip to weaken the steel to make it brittle. Okay? The nice thing about hydrogen cracking is it's reversible. You can get the hydrogen in the steel, but if you get it out before a crack forms, no harm done. Okay? What do you have to do? Well, for example, the ASTM spec for electroplating, because there's different ways to get hydrogen into steel. You can get it from welding, you can get it from corrosion. Okay, corrosion breaks down, if you have 1.1 volts, you can break down the water into hydrogen and oxygen, and that stuff can go right in the bolts. I've had plenty of bolts, steel bolts and high-strength steel bolts in seawalls, and people want to know why the heads are breaking off the bolts. Well, you're in salt water, and if you have it galvanically coupled to something else, and anyway, I mean, was it, yeah, you were, no, one of you had some galvanic, who had the galvanic oh, is the titanium pipe. You had the galvanic coupling, okay? You're going to be generating hydrogen. And that hydrogen will get into the steel and can embrittle it. Now, you were looking at corrosion, but if you had stresses in there, you could have cracked it, okay? I've had 3 or 4 times, I've had someone come to me with a seawall they built at some port, and the heads of the bolts are coming off after 6 months. Okay, they say, oh, must be defective bolts. No, it's corrosion, and it's generating hydrogen. There wasn't any hydrogen in these bolts when they were made, but you generated it from corrosion. So you can get it from welding, you can get it from corrosion, you can get it from electroplating. Okay, electroplating is kind of better known by, well, the welders all know about the hydrogen. The corrosion guys all know about the hydrogen for corrosion. The welders know about the hydrogen from welding, and the electroplaters know about it for electroplating. The spec from ASTM says that you must put it in the furnace within 1 to 4 hours for electroplating to get rid of the hydrogen. Why? Well, I just went through the calculation here, roughly. You know, if you don't get it in there within an hour, it's liable to migrate and diffuse to those crack tips, a millimeter or whatever, to whatever the imperfection is, and the thing could crack. Now, if I have a bigger section, you know, if I'm building a 100 KSI strength bridge, which has 120 KSI, I'm not allowed, per the D11, the bridge welding code of AWS, I'm not allowed to do my non-destructive testing for 48 hours or 72, I can't remember. I think it's 48 as I think about it, because I might have had a crack form. But in 48 hours, most of it will have diffused out. And so I'll be okay. I shouldn't expect cracks after that, okay? At that strength level, okay? If I have a higher strength part, I really, the code says, the ASME standard, it's not a code, says you got to put it in within 1 to 4 hours, and you either heat treat it for 4 hours at 375 degrees Fahrenheit. Where did they get 375 degrees Fahrenheit? I don't know. Calculate it in centigrade and see if it came from Europe or the United States. I don't know, but 375 sort of works as a high enough temperature from a plot like this. 375 is probably something like 200, and you're getting up here to almost as good as unnotched, okay? So far as that goes. You either do it for 4 hours at 375 within an hour to 4 hours so that you get it into the furnace, and then you hold it for 4 hours, or you do it for 23 hours. Now, where did 23 hours come from in a heat treating shop? Think about it, think about it. Next shift, you got 1 hour to take one load out of the furnace and put another one in. So whoever wrote this standard realized you have to load and unload your furnace. So they said 23 hours is the standard. They could have said 24 hours, and you would just creep up into the next shift after, you know, so eight days or something, right?
So I know the codes are put together by committees to the
Yeah.
ASME, the committees for the
Yeah.
writing of standards. So
Oh, yeah.
they probably had industry guys who said,
Exactly.
we're doing it for 25 hours.
Right. But I mean, when you see something like that, be curious. Ask yourself the question, well, why would someone pick 23 hours? Okay? Anyway, well, that's why they picked 23 hours. Let me show you something else. Now, this is a hydrogen stress corrosion, high strength low alloy steel, time for sulfide stress corrosion cracking. Sulfide cracking in, like, the oil industry is H2S, hydrogen sulfide. That's what they mean by sulfide stress corrosion cracking. What's the product if the sulfur reacts with your steel? You get hydrogen. This is just a corrosion source of hydrogen. They got all kinds of, well, in Texas they generally have sweet gas. But in other parts of the country we have sour gas. Now, I had never been through Evanston, Wyoming. Anyone from Wyoming? Almost no one's from Wyoming. It's the least populated state in the country, okay? But Evanston is just sort of at the corner. You know, Utah's got this funny shape and it's got a little notch cut out of it. That's Evanston right there in the notch, but it's on the Wyoming side. And it's a ranching area and there's lots of cows. And you drive through the farm area, the cow area of Evanston. In fact, I had to wait for a cow to cross the road. I mean, there's no fences there. They just kind of wander anywhere. But you also see these signs as you're driving through this tumbleweed type area. It's not exactly tumbleweeds, it's rolling hills, but they don't have trees. They got little scrubs of grass, which I guess the cows have to eat. Anyway, it says, danger, toxic gases. Well, it turns out they're on top of a gas dome in that area, which has got up to 17% hydrogen sulfide in it. And hydrogen sulfide, it's actually, the reason it's toxic is because at first it has a terrible smell, apparently. Don't remember. Actually, I guess it sort of smells like rotten eggs, but rotten eggs are really sulfur dioxide. But it has sort of a rotten egg smell. But then it numbs your olfactory nerves. And so you can get a huge dose of it and never know it, because you basically anesthetize your nose. And so you can get an overdose of hydrogen sulfide. And so you're driving, it's the first place I'd ever been about danger, toxic gases coming up out of the ground. They just percolate out of the ground because some gas companies, Chevron and Amoco and I think Chevron, started about 30 years ago drilling for gas there. And because it was a great source of gas, and this, anyway, but they had to get the hydrogen sulfide out, and they actually, one of them built a sulfur pipeline that would take it to the rail station. Because sulfur is a valuable commodity. They make sulfuric acid, right? I told you sulfuric acid is the largest commodity of any acid, basic chemical that we use. One of them built a heated pipeline to pump the sulfur out of there, and the other one had big trailers of liquid sulfur and semis, and they built a 10-mile road to the railhead to just truck it. And so it's just two different companies, two different choices of whether you want to pay drivers a long time or the other one build a pipeline and get the people out of it. But hydrogen sulfide can cause cracking because of sulfur, but not because of sulfur, but because of the hydrogen. And here is a little bit more quantitative plot than Coe's sort of schematic plot. And where is, these are data points, where is the shortest time and what time is it? It's just over 1 hour at room temperature. I mean, 20 degrees C, okay? We live in the worst possible temperature for hydrogen cracking, okay? If you live in the Arctic, or I might tell you on Monday a story of hydrogen crack where it got buried in the snow in the high Sierras, and it lasted for 9 months in the steel, okay, before it did its damage, okay? Or you can heat it up to 100 degrees C and drive it off, you know, at in a reasonable number of hours to get rid of it, okay? Diffuse it out. Just like Sprite, you have warm Sprite, you boil your Sprite, no CO2 left, right? No hydrogen left either. Okay, so where are we now? We've done that, we've done that. We covered all that. Okay, so what do we do when we're trying to understand all three of these plots? I lost my plot. By the way, Dustin is going to start helping me organize some of these things. I finally decided to have someone, that's Dustin, raise your hand. Okay. He's also the one putting things on YouTube and stuff, although we have to find some other things to do. But I have my little Venn diagram of this stuff. I can't find it right now, but I got stress, material, and environment, or whatever the thing is. One of the things I have to get rid of is some of the stress. But how do I even simulate it? Well, if you go back to Stout and Doty's book, which is where this thing came from, there's lots of ways to try to simulate it. When I worked at Bethlehem Steel, and one of the other engineers had a hydrogen cracking project, we had some like 3-inch thick plate, and we cut a little window in it, and we put like 2-inch plates up against that, and we would put the steel we wanted to test as a vertical piece, and we'd essentially have this 3-inch plate with a little window, and we'd weld it into this 3-inch plate so it's completely restrained, right? And they had strain gauges on it to try to quantify everything. So far as that goes, lost my pointer too. This one's working. Well, there's simpler tests. There's this is called the CTS, Controlled Thermal Severity Test. I think it was actually invented by the Navy at one time. But you basically put one little plate on another plate, you bolt them together, you put a fillet weld on 2 sides, and then you actually measure your trithermal weld. Okay, so by trithermal, you basically have welded these 3 sides. This is like putting the 4th side on a 4-sided box, right? I talked about a 6-sided box in restraint before for a 3-dimensional box. This is the test weld, and you've got this other plate sticking off here. To put lots of restraint on this, there's nowhere for this weld to shrink, right? So they call that controlled thermal severity. There's all kinds of tests. There's the cruciform test. You basically put 2 plates on top of another plate. You weld all 3 of them, tack weld all 3 of them together on these end welds, and then you put in 1, 2, 3, and 4. And then the 4th one is the one you're really testing, because that's the one, there's nowhere for it to bend, okay? You're putting in now, hopefully, full level residual stresses. The Japanese had one they called the Tekken test, T-E-K-K-E-N. Tekken means railroad in Japan. So guess what industry this came out of? They used to call it the Y-groove test. And the reason they liked it is because it was easy to flame cut. You basically take your 2 plates and make a Y with the joint preparation. And then you put a weld right in here, and they found they could really, that was a terrible geometry in terms of residual stresses, and they could get hydrogen cracking. So in Japan, they'll talk about Y-groove tests or Tekken test. That was their test. There are literally dozens of these type of little laboratory tests to try to simulate the restraint that you get in a real welding situation. They all sort of work, but that also means they all sort of don't work, right? Anybody have any questions?
So what are you measuring actually?
You're just looking for a crack. You put a weld in, and then you cross-section it and say, is there a crack there? You can do dye penetrant. You know, the crack might be under bead, so you may have to section it to find the crack. But you just weld these things and you look for a crack. Typically magnetic particle, dye penetrant, cross-sectioning. You just weld it and see if you get a crack. Pretty empirical, but that's sort of the level they do it. Okay. There is another test that the French developed, which is a little more scientific. It's called the implant test. And you basically just take a plate and you put a hole in it. That's easy to do. And you take the steel plate that you want to test and you make it into a screw with a thread on it. Okay? You put the screw up through the hole and you weld the top of the end of that screw to the plate. Just put a weld bead on top. And so I've got the screw sticking through the thing, and you put a weld bead on the top so it's welded. And then you put it in you load it. You take the head of the screw and you pull on it with a known force. So now you actually know how much stress you have on that screw. You have a certain amount of hydrogen from your weld metal and your plate, and you have the heat affected zone of the plate on the screw because the heat had to, to come down the screw. And you hold it there, and what I haven't told you is, well, I have told you sort of, hydrogen cracking is also known as delayed cracking. It takes time, okay? It doesn't happen immediately while you're welding. It doesn't just pop, right behind you, seconds behind you. It might take an hour, it might take a day, it might take 3 days. The Navy waits, and HSLA, and actually their HY steels, they wait 7 days before they let someone do a test to look for cracks, because they want to make sure that any crack that wants to grow has time to do it, because they want to find the crack when they inspect, not inspect and then have a crack occur that they don't know is there. Okay, so we have these little tests, but it's called delayed cracking. And so I I mean, I see this about once a year. Someone comes to me and they say, we found a crack. In fact, I should have brought it with me. I have a Farberware pot. I can tell this story in a couple of minutes we have. So I have a stainless steel Farberware pot that in my office. Maybe I'll bring it in on Monday. And about 20 years ago, MIT has an industrial liaison program, and Farberware, who was making these pots, came in with this problem. They can consult with the faculty member for 1 hour, and it doesn't cost them anything more than about $80,000 a year to MIT. And the faculty member will get $80 in discretionary funds for spending an hour talking to these people. Well, I used to do this. In fact, I used to do this more than anybody else on the faculty in the 1980s. And so Farberware came in. This is a big cooking pot, and it's got a slippery, a non-stick coating on the inside. And they had cracks along the side. And they said, when they left our factory in Brooklyn, and I had to go to the factory in Brooklyn, let me tell you, you don't want to have to go to that factory. It's not the nicest area of Brooklyn. I was there in a snowstorm. Anyway, there's only one door in this huge factory. I had to walk all the way around it to find the one entrance. And I was afraid I was going to get mugged and left bloody in the snow the whole time. Anyway, they come in and they say, we have these cracks. And they had a pot. And they left the pot with me. And I've been showing it to students and they had cracks. And they said, when it gets to Japan, gets off the boat in Japan, a couple of weeks later, it has these cracks in it along the side. And I said, well, let me show you something. So I went and got a magnet, which I have a number of magnets in my office, and I just went up the side of the pot. Can I use your cup? So I'm going up the side of the pot with the magnet. No magnetism down here because it's the austenitic stainless steel, face-centered cubic. It's 304 stainless steel. And you go up, and all of a sudden it becomes magnetic. Turns out 304 stainless steel, if you deform it, will transform to martensite. Well, I knew that. I'm a metallurgist. Okay, that's why you come to me. And it turns out you go up the side, and I'll bring it in next time, and you can take that same magnet and go up the side, and you find it's very magnetic up here where the whole thing had been formed to make the cup. I said, you've got martensite. Well,